Gases, understanding gas laws and applying them to the real world. Application, gas laws, explain the relationship between a gas's pressure, volume, temperature, and amount that applied in real-world situations like weather forecasting by meteorologists, refrigeration and air conditioning by engineers, scuba diving safety, the design of engines and gas system, medical applications such as administering anesthesia and oxygen. Definition of pressure. Pressure is the force exerted by gas particles colliding with the walls of their container, divided by the area of that surface. This pressure results from the countless collisions of the rapidly moving gas molecules with the container's surfaces, creating a continuous force over that area.
Boyle's law. At a constant temperature, pressure and volume are inversely proportional. Let me give you an illustration first. So imagine if we have a column where the volume can be adjusted. And let's say there's some gas particles inside of it. So I'm not going to put too many, maybe like 7 gas particles. Now let's say if we apply a force to compress this container in order to decrease the volume. So now the volume is greatly decreased. And we're still going to have the same 7 molecules. So now, what can you tell me about the pressure inside of this container? Is it greater or less than the pressure in the first one? So in this container, the volume is relatively high, and here, the volume is low. So as we decrease the volume, what happens to the pressure? Now notice that in this container, the particles are more spread out, and so they collide with the walls of the container less frequently. Here, all the particles are bunched up together. There's not much space between the particles, and so they collide with the container more frequently. It turns out that the gas pressure is proportional to the number of collisions. So therefore, the pressure is higher in this container, and it's lower in that container. And so this is the basic idea behind Boyle's law. Pressure and volume are inversely related. If you decrease the volume, the pressure will increase. And likewise, if you increase the volume, the pressure will decrease. So the pressure of a gas inside a container, given that if temperature is held constant, is dependent on the volume. If you decrease the volume at constant temperature, the pressure will increase. If you increase the volume at constant temperature, the pressure will decrease. And that's Boyle's law. Now, the equation that is associated with Boyle's law, you need to know what it is this equation. P1 times V1 is equal to P2 times V2. So this is the equation that you're going to use when solving volume and pressure problems. Now you need to know the shape of the graph that is associated with Boyle's law. So let's say if we plot pressure on the y-axis and volume on the x-axis. We know that as the volume increases, the pressure should decrease. Now, do you think the graph is going to look like this? It's not going to be a straight line. Rather, it's going to be a curved line. As the volume increases, the pressure will decrease like this. So that's the correct shape for this type of problem, or this type of law. You might see this in a multiple choice practice test. You might be given maybe 4 or 5 graphs and need to know which one is associated with Boyle's law. So make sure you know the shape of this graph. Now let's work on some problems. Number 1, a 2.5 liter container has a gas pressure of 4.6 atm. If the volume is decreased to 1.6 liters, what will be the new pressure inside the container? Well, let's make a list of what we have. Not sure what just happened there. So V1, the first volume, is 2.5 liters, and a pressure that corresponds to that volume is 4.6 atm. Now the volume is decreased to 1.6 liters, so that's a new volume, V2. And we're looking for the new pressure, P2. So all we need to do is use this equation. P1 V1 is equal to P2 times V2. So P1 is 4.6 ATM. V1 is 2.5 liters. Our goal is to calculate the value of P2, and V2 is 1.6 liters. So 4.6 times 2.5, that's 11.5. And that's equal to 1.6 times P2. So now, to solve for P2, we got to divide both sides by 1.6. So P2 is 11.5 divided by 1.6. And so that's about 7.19 ATM. So as we can see, in line with Boyle's law, you should always check to make sure that this answer makes sense. We decreased the volume from 2.5 to 1.6. So therefore, the pressure should increase from 4.6 to 7.19.
Charles' law, at a constant pressure, volume and temperature are directly proportional. In this video, we're going to talk about Charles' law. Charles' law describes the relationship between volume and temperature. So what happens to the volume of a gas if you increase the temperature? Will it go up or down? So let's say if you have a balloon at a temperature of 300 Kelvin, and let's say it's a 2-liter balloon. Now what's going to happen if you double the temperature to 600 Kelvin? What's going to happen to the volume of a balloon? Whenever you heat a gas at constant pressure, the volume of the gas expands. So the balloon is going to be 2 times as large. It's going to be 4 liters. And that's the basic idea behind Charles' law. It shows the direct relationship between temperature and volume. If you increase the temperature, the volume will increase. Likewise, if you decrease the temperature, the volume will decrease. So these two are directly related to each other. So let's say if you were to make a graph between volume and temperature, it will look like a straight line. It's a linear relationship. So as the volume goes up, the temperature, the Kelvin temperature goes up with it at the same rate. Now, the equation that is associated with Charles' law is this equation. It's V1 divided by T1 is equal to V2 over T2. So that's the formula you need to know when solving problems associated with Charles' law. Now let's put what we learn into practice. So let's try this problem. A 3.5 liter flexible container holds a gas at 250 Kelvin. What will the new volume be if the temperature is increased to 400 Kelvin? So let's write the information that we know. The original volume V1 occupies a space of 3.5 liters. And it occurs at a temperature of 250 Kelvin. Our goal is to find V2. We need to calculate its value. And the new temperature is 400 Kelvin. So all we got to do is plug in the information into this equation and solve for the missing variable. So V1 is 3.5 liters. T1 is 250 Kelvin. We're going to just rewrite V2, that's what we're looking for, and T2 is 400 Kelvin. So the best thing you could do in this problem is cross multiply. So 3.5 times 400, that's 1400. And that's equal to 250 times V2. Now the next thing that we need to do is divide both sides by 250. So V2 is 1400 divided by 250. And so you should get 5.6 liters for the volume. So as you can see, as we increase the temperature from 250 Kelvin to 400 Kelvin, the volume increased from 3.5 liters to 5.6 liters in harmony with Charles's law. Anytime you increase the temperature, the volume will increase. Gay-Lussac's law. At a constant volume, pressure and temperature are directly proportional. Gay-Lussac's law. So what's the gist of this law? What's the main idea behind it? Well, let me give you an example to illustrate it. So let's say if you have a container with some gas particles, and this is going to be a rigid container. Its volume is fixed. What's going to happen if you add heat to this container? What's going to happen to the pressure inside? Will the pressure increase or decrease? According to Gay-Lussac's law, anytime you increase the temperature, the pressure will increase if the volume is held constant. If the volume is allowed to expand proportionally to the temperature, then the pressure could be constant. But if you have a fixed container with a fixed volume, like a rigid container, if you increase the temperature, then the pressure has to go up. Now, how does that work exactly? Well, as you add heat to the molecules, these molecules will gain kinetic energy, and so they will be moving a lot faster at a higher temperature. As a result of the increased speed, they will collide more frequently with the walls of the container. And anytime you can increase the number of collisions, you will increase the pressure inside the container. So that's how an increase in temperature leads to an increase in pressure. Higher temperature causes molecules to move faster, which increases the number of molecular collisions, which leads to a higher pressure. So that's the gist of Gay-Lussac's law. Temperature and pressure are directly proportional. If you decrease the temperature, the molecules will lose kinetic energy, they will travel slower, and so there's going to be less molecular collisions, so the pressure will decrease. Now let's plot temperature on the x-axis and pressure on the y-axis. The shape of the graph is a linear shape. It's simply a straight line going up. So make sure you know this shape, by the way. You might be tested on it on your next exam. Now the equation that goes with Gay-Lussac's law is this equation. P1 over T1 is equal to P2 over T2. So this is the formula that you need to use. Now the pressure has to be in the same units. It could both be in torr, atm, kilopascals, psi, millimeters mercury. It simply has to match. Now the temperature has to be in units of Kelvin, not Celsius. And so if you're given the Celsius temperature, convert it to Kelvin by adding 273 to it. Now another illustration of Gay-Lussac's law at work is if you have a pot. So let's say you have a pot and you put some water in this pot. And then you place the lid on the pot. And then after that, you put the pot on a stove, so you heat it up. What's going to happen to the pressure inside? As you heat up water, some of the molecules will vaporize into steam. And as a result, you can have a buildup of gas above the surface of the fluid. And as the pressure increases, eventually, when it gets hot enough, that pressure will be strong enough to lift off the lid of the pot. And so as the temperature increases, the pressure will increase. And in this example, there's going to be a limit. Once the pressure reaches that threshold, it will be strong enough to lift off the pot. And so it can relieve the pressure once that steam comes out. So that's another example of Gay-Lussac's law at work. Now let's work on some practice problems. The pressure of a gas in a rigid container is 125 kilopascals at 300 Kelvin. What will be the new pressure if the temperature increases to 900 Kelvin? So now let's think about it conceptually. We know that if the temperature increases, the pressure will increase proportionally. Now the temperature increases from 300 Kelvin to 900 Kelvin. So basically, it increases by a factor of 3. 300 times 3 is 900. So therefore, the pressure should increase by a factor of 3. So 125 times 3 will give us a final pressure of 375. So if the numbers are nice and easy to deal with, you can calculate the final pressure mentally. Now sometimes you might have a problem that doesn't have nice numbers like this. So let's get the same answer using the equation. So let's make a list of what we have. T1 is 300 Kelvin. And the first pressure, the original pressure, that's 125 kilopascals. T2, the new pressure, the new temperature rather, that's 900 Kelvin. And our goal is to calculate the value of P2. So we're going to use the equation P1 over T1 is equal to P2 over T2. If you flip it, T1 over P1 equals T2 over P2, you'll get the same answer. So P1 is 125 kilopascals. T1 is 300 Kelvin. And T2 is 900 Kelvin. So what I like to do at this point is cross multiply. So 125 times 900. That's going to be 112,500. And the units I currently have is kilopascals times Kelvin. And then that's going to equal 300 Kelvin times P2. So now let's divide both sides by 300 Kelvin. So on the right side, all I have left over is simply P2. On the left side, the Kelvin units will cancel, which means the unit for P2 is going to be kilopascals. So 112,500 divided by 300 is equal to 375 pascals, kilopascals. So that's how you can use the formula to get this answer.
Avogadro's law. At a constant temperature and pressure, the volume of a gas is directly proportional to the number of gas molecules. Avogadro's law. So what do you think is the main idea behind Avogadro's law as it relates to gas laws? Avogadro's law describes the relationship between moles and volume. So, what's going to happen to a balloon, the volume of a balloon, if you blow in more moles of gas or air into a balloon? As you increase the number of moles of air in a balloon, the balloon will expand. So, as you increase the number of moles represented by the letter N, the volume will increase. The more air that you blow inside the balloon, the bigger it will become. And moles is basically quantity. Think of a dozen. A dozen represents 12. So a mole is 6 times 10 to the 23. It's a very large number. Now let's say if you have a balloon that contains 1 mole of air. It's going to have a volume of 22.4 liters. Now let's say if you have 2 moles of gas, the volume is going to increase to 44.8 liters. So as you increase the number of moles of gas, the volume will increase. So the equation that you need to know that goes with Avogadro's law is this equation. V1 over N1 is equal to V2 over N2. So that's the formula that you're going to use when solving gas law problems that deal with moles and volume. Now V1 and V2, they can be in milliliters or liters, but they simply have to match. So if V1 is in milliliters, then V2 should be in milliliters as well. Now the graph that goes with Avogadro's law, if you plot N on the x-axis and V on the y-axis, it's a direct relationship, so it's just a straight line. Now let's work out a few problems. If 2.4 moles of gas occupies a volume of 60 liters at a certain temperature, what volume will 3.7 moles of gas occupy? So let's write down what we know. N1 is 2.4 moles, and the volume that corresponds to that, which is V1, that's 60 liters. N2 is 3.7 moles. Our goal is to calculate V2. So let's use the formula V1 over N1 is equal to V2 divided by N2. So V1 is 60, N1 is 2.4. V2 is, we're looking for that, and N2 is 3.7 moles. So what we need to do is, we need to cross multiply. So let's multiply 60 by 3.7. So that's going to be 222. And that's equal to 2.4 times V2. So now we got to divide both sides by 2.4. So V2 is 222 divided by 2.4. And so that's going to be 92.5 liters. And so that's the answer. So notice that we increased the moles from 2.4 to 3.7. And the volume increases from 60 to 92.5.
Ideal gas law. A combination of the above gas laws, PV equals nRT, which relates pressure, volume, the number of moles, a constant, and temperature.
A 2.5 liter container holds 0.45 moles of nitrogen gas at 315 Kelvin. What is the pressure inside the container? Well, let's write down what we know. So we know the volume is 2.5 liters. N represents the number of moles. That's 0.45 moles. And the temperature is 315 Kelvin. Our goal is to calculate the pressure. So we could simply use this formula. PV is equal to nRT. Our goal is to calculate P. V is 0.45. Actually, no, V is 2.5. N is 0.45. And R is 0.08206. And the temperature is 315. So let's multiply 0.45 times 0.08206 times 315. So that's equal to 11.632. Now, to get P by itself, we got to divide both sides by 2.5. So it's 11.632 divided by 2.5, and that's going to give you a pressure of 4.653 ATM. And so this is the answer to this problem.
In summary, gas laws define how a gas's pressure, volume, temperature, and particle amount relate, and these principles are applied in real-world situations to solve practical challenges.